We were to discuss about what is numerical aperture. So this is, you're able to see what I'm sharing, right? The ray theory transmission.
Yes, sir.
Yes, sir.
Yeah, I have already shared two books and one another slides which I was sharing yesterday. So this is from the second book, Optical Fiber Communications Principles and Practices by Senior. So here you can see a side view of an optical fiber, and at the on the left it mentions an acceptance cone. You can see a conical part, right, with an angle given as theta A, which is given as the conical half angle. What is meant by this acceptance cone and the conical half angle is if the angle of incidence of any light ray is greater than this theta A, then that light ray will be lost in the cladding. It will go into the core, but from the core it will go into the cladding. I hope that is understandable. You can see there are two rays which are given here. One is A, one is this A, another one is can someone help me with this Microsoft Edge? I've presently, okay, I've come back. Yeah. Yes. So in this, you can see two rays that are here, A and B. Fine. Now these two rays ray A is within this conical half angle theta A. So it goes into the core, and once inside the core, at the core cladding interface or boundary, you have total internal reflection, and this goes or this propagates along the fiber. Now if you look at this ray B, it is outside of this conical half angle, so it does go into the core, but after it goes into the core, you do not have total internal reflection. What you have is refraction from core to cladding, and eventually this type of rays are lost in the cladding. So information carried by ray B is lost in the cladding, and it would not be available at the receiver, which is after a very long distance, maybe around 1 kilometer or 20 kilometers or even 100 kilometers. So it can be any distance that would vary according to what a designer needs to work on. Uh, so you're able to understand what is theta A, right? So if we have an incident ray which has an angle greater than theta A with the normal to the surface of the normal to the surface of the fiber. This is the normal, right? Normal to the surface of the fiber. Then if the angle is greater than theta A, it will be lost. Okay. So within an angle theta A, you can expect transmission of the light ray in the fiber. I hope this is clear. Now, yes. So if you look at this other angle, phi C corresponds to the total internal reflection that has occurred at the core cladding interface. That is this. Fine. So at this core cladding interface, if the angle phi C is, how do I put it? If this is less, means lower the angle, you can expect total internal reflection not to occur. Okay. So this phi C must, the C here corresponds to the critical angle at which you will have total internal reflection. Okay. So if this angle is less than phi C, then you would have refraction at the interface and not total internal reflection, right? So based on this, there are there's a small derivation about how you can find numerical aperture. So from air, the refractive index here is given as N0, and here you have the core refractive index as N1 and cladding refractive index as N2. This N2 is not on two sides, but it's in a cylindrical form. Fine. And theta 1 is your angle of incidence, and theta 2 is your angle of refraction. Okay. And phi is your total internal reflection which has occurred at the core cladding interface. And based on this, you're familiar with Snell's law, right? So according to Snell's law, you have N0 sine theta 1 equals N1 sine theta 2. That corresponds to this interface. N0 and sine theta 1 and N1 with sine theta 2. Okay. This is the same Snell's law. Clear? Going forward, consider the right angle triangle ABC. You can see the points A, B, and C, right? This is a right angle triangle. So here you know the sum of the angles within a triangle is 180 degrees. So theta 2 plus phi must be equal to pi by 2, right? So based on that, we have phi is pi by 2 minus theta 2. And we have N0, so theta 2 here is replaced with, in terms of phi. We have, instead of theta 2, it becomes pi by 2 minus phi. And sine of pi by 2 minus phi becomes cos phi. Clear? And we have the trigonometrical relationship sine squared phi plus cos squared phi equals 1, which is a universal relationship. And based on that, this cos phi is replaced by square root of 1 minus sine square phi. So this comes from this. Okay. And if we consider the limiting case for total internal reflection, then phi becomes equal to the critical angle for the core cladding interface. The core cladding interface corresponds to this line. Okay. So at phi c, we have an angle of incidence and the angle of what is it? You can say total internal reflection, or this particular phi would be equal to 90 degrees. Okay, this would be along the core cladding interface. I hope that is clear. Now, so phi becomes equal to the critical angle for the core cladding interface, and in this limiting case, theta 1 becomes the acceptance angle for the fiber, which is theta A, the half conical angle. And when we combine these limiting cases, we get this expression n0 sine theta A equals n1 square minus n2 square square root. I hope you are able to get this, and this is what is known as the numerical aperture, NA. Is this clear to all?
Yes, sir.
Yes, sir.
Okay. Now there's an interesting term, which is the relative refractive index difference, and the symbol used is delta for this. And the relative refractive index difference is usually given by this expression, n1 square minus n2 square by twice of n1 square. So the denominator is the core refractive index, and what you see as an approximation as n1 minus n2 by n1, this is an approximation which you get from the numerator side by splitting it into fractions n1 minus n2 and n1 plus n2. Since n1 and n2, the values are very close to each other, the typical value of n1 is of the order of around 1.5, and if the n1 is the core refractive index. So if n1 is 1.5, the cladding refractive index is usually chosen slightly lower than that and would be probably around 1.49 or 1.48. So the difference between n1 and n2 is hardly 0.01 or 0.02. So that is the usual difference that is there between the core refractive index and cladding refractive index. So when we have n1 minus n2 and n1 plus n2, n1 plus n2 can be approximated as twice n1. Okay, so if we do that approximation of twice n1, then from the denominator, twice n1 cancels out with the twice n1 that we approximate in the numerator. N1 plus n2 approximated as twice n1, and the denominator side twice n1. So the resultant, this is an approximate value of the relative refractive index difference. Clear? Now there's another parameter, delta n. This is referred to as the index difference. This is not the relative refractive index difference. Okay. So delta n, and what we have here is delta. Okay, this is delta. I hope you are able to identify the difference. What is relative refractive index difference and what is just the index difference. Okay. So if we approximate these, then delta n by n1 you can say is, because n1 minus n2 is delta n, right? So this is delta n by n1. So delta, or the relative refractive index difference, can also be given by delta n by n1. Clear?
Yes, sir.
Fine. So if we combine the above equations, the numerical aperture and the relative refractive index difference, okay, so we have the numerical aperture as n1 square minus n2 square square root. So this n1 square minus n2 square root can be approximated with n1 and 2 del square root, 2 delta square root. I hope you can, this is simple algebra which you can follow. So this is a simple example of how you can identify the refractive index difference.
Surrounding noise बहुत ज़्यादा है.
क्या हुआ?
आवाज़ें आ रही है पास से.
Well, there is some. We have a meeting in the adjacent room. So it should take about 5 minutes or so before it is done. So just let me scroll through what we have here. This is a simple example. You can find out, given the parameters, you can find out what is the half acceptance cone and what is the numerical aperture and what is the critical angle at the core cladding interface. So you can go through all these. I've already shared this book with you. Now, skew rays are something which are very typical, and you can see what we have seen to identify the numerical aperture and the conical half angle is different from this. Okay, this is not a ray which is propagating along the axis of the core. You can see there is a line along the core. This is the axis. So this particular ray is incident at a point which is not at the axis, but it is away from the axis. And based on the angle of incidence, it is able to propagate along the fiber. It is able to propagate along the fiber, but it goes in a helical, or you can say like a spring, in the shape of a spring. I hope you have all seen the shape of a spring. So if you look at from the surface of a fiber, this is what you would see. The path of transmission of the fiber would be something like this. Okay, there is total internal reflection at the core cladding interface, but it is not at the same the length, meaning you have a total internal reflection which is happening here, and another here, and another here, and here, and here, and here, and here. So these are different points along this. So these are all the points. Okay. So this is how this is what is known as a skew ray, and it does not propagate along the axis of the core. Fine. So if you want, yes.
So how to ensure that every time the incidence angle is greater than the critical angle?
How to ensure?
How to ensure that every time the incidence angle of the ray is greater than the critical angle?
The critical angle at the core to cladding interface?
Yeah, sir, yeah.
Yeah, so for that, you need to look at this. So if this would be your phi c, right? At an angle phi c here, you would have the ray, the incident ray would go along the core to cladding interface. So that is a very critical condition. So usually it is necessary that we have total internal reflection. So this phi c must be yes. So the phi c, the angle phi c must be greater than that. So this angle phi must be greater than that phi c. Only when this angle is greater than phi c, then you would have this total internal reflection. Okay. So when phi is larger, meaning this ray is coming at an incidence which is lower than this, something like this. Okay. Then you would have total internal reflection. Fine. And in order to have this, you have refraction at this interface, right? Air to core interface. So here we have found this the relationship between θ1 and θ2 using the Snell's law. So based on this, we have found out what is the relationship between θ2 and phi. So when we substitute phi with phi c, then θ2 we get as the critical angle at which we will have total internal reflection. So based on θ2, we get the identifying angle θ1 at which it will support total internal reflection. So here θ1, the angle or the maximum angle of θ1 at which we would have this total internal reflection. That is what is known as the half conical angle or the acceptance angle. Does it clarify things?
So actually, I was asking about subsequent reflections that will happen to the particular same ray, not about only first reflection.
Subsequent reflections, as long as
multiple reflections.
Yeah, as long as the fiber is along a straight line. Okay. If the first reflection is total internal reflection, then subsequently also you will have total internal reflection. I hope that is clear. As long as it is straight.
So what if it is not straight?
Yeah, if it is not straight, then you have to ensure that the angle of incidence, if this is my theta A, then your angle of incidence is much less than theta A. Is that clear? So this is about Q rays, and if you're interested, you can also take a look at what would be the acceptance angle for the Q rays. So this is a slightly more complicated derivation. Now, yesterday also I had mentioned you about that the light which is propagating in the fiber can be or you can say you can consider the light propagating in the fiber as a ray or as a wave. So if we consider the light propagating in the fiber as a wave, then we look at it as an electromagnetic wave, and we come down to the Maxwell's equations to identify what would be the wave function. And these are the standard expressions that you have for the Maxwell's equations with no free charges and no free poles. And this substitution, I believe you are able to understand these, right? Del cross E and del cross H, right? This is about taking the curl of these. If you take the curl of this and this, of these two expressions, then you get these. And using divergence conditions, you can come down to this simplified expression. Del square E as mu epsilon dou square E by dou T square, and del square H as mu epsilon dou square H by dou T square. And this psi is corresponding to the wave function. This can be E or H. To generalize the derivations, means you can see here that both expressions, del square E and del square H, are similar, right? So if E and H can be replaced by this psi, then you need not solve these equations separately. You can use this single expression to represent both, and this would help us to simplify the derivation. So psi represents it can represent either E or H. Okay. And Vp is the phase velocity, which is given by 1 upon mu epsilon square root. And the velocity of light in free space, that is given by C, is 1 upon mu naught epsilon naught square root. Now, planar waveguides. Yesterday I talked about planar waveguides. A planar waveguide would be a sort of I hope you are able to understand this cuboid structure, right? In a cuboid structure, you can have light transmission and you can have total internal reflection and light going out. So this would be a planar waveguide. The planar waveguides are used in some specific cases wherein it becomes easier with multiple layers and multiple materials. Okay, but usually these planar waveguides are used when the dimensions are much smaller than what we have for the optical fiber. Fibers, the dimensions that we normally use is of the order of kilometers, whereas the planar waveguides which are used, these are of the order of millimeters and centimeters. It does not go beyond that. So you're already familiar with the, well, here this particular expression of the wave function. This can be solved by using either the Cartesian coordinates or the polar coordinates. So based on what is used, it can be different. So if we are working with a planar waveguide, then this is what is preferred. And if you are working with a cylindrical waveguide or an optical fiber, then this is what is preferred. Okay. Now, if you consider an electromagnetic wave that has this standard form, so this standard form is necessary to represent an electric field or a magnetic field. So omega t represents what is the frequency and with time how it changes, and k dot r represents what is the propagation of the wave along the waveguide. So I think you're already familiar with this phase propagation constant k, right? You must have gone through this in your physics classes. And if you look at the modes in a planar waveguide, so here we have beta x, beta z. X and z are the directions which are given in this fiber. Fine. So z is the direction of propagation. Okay. So beta is what is known as the propagation vector, and this propagation vector can be split into its different components. So what we have here is beta x and beta z, and of course it's not necessary that it should be limited to this. If we consider some rays which are not propagating within this plane, within the xz plane, then there can also be a beta y. Okay. So this is the simplest case, so it is easier to analyze. And this figure shows how you have two rays which add together as an electric field. So this shows the propagation of the electric field along the z direction. So these are the components of the propagation constant. So yeah, yesterday I mentioned about the transverse electric modes, right? So this is these are different modes which you which can propagate in a optical fiber. Okay, so what is referred to as the guide is the core, and we have the cladding, and this particular mode is present on both sides of the axis. And if you look at the output light which would come out of this fiber, there would be two spots. Okay, so that corresponds to this TE1 mode. And this T2 mode would have three spots corresponding to these three peaks. Okay. And as you look at higher order modes, the intensity of light along the fiber, this intensity would be reducing in the core and the intensity in the cladding would go on increasing. So here also you would be seeing three bright spots corresponding to the three peaks that you have here. So this is about two waves with nearly equal frequencies. Then you have a group velocity. So the phase velocity is given by omega by beta, and this group velocity is given by del omega by del beta. Beta, or the propagation constant, is given by n1, the core refractive index, into 2 pi by lambda, and this is also n1 omega by c. I hope you are familiar with these conversions, right? Lambda is c by f. Fine. So in this, if you substitute lambda is equal to c by f, you can come to this. You're familiar. I hope you're familiar with the angular frequency. 2 pi f is given by omega, right? So the phase velocity is given by c by n1. I hope you are also familiar with this. N1 corresponding to the refractive index of the core, and c corresponds to the velocity of light. So the phase velocity represents the velocity at which a light ray would propagate in the fiber. Clear? So this would be possible when the light ray has a single frequency. But as with most practical things, any light ray, it is very difficult to have a light ray which has a single frequency. Well, you can say impossible, but I would prefer not to use the word impossible, but it is next to impossible to have a single frequency to propagate along the length of the fiber. So whatever source we use has a very narrow line width or bandwidth. It has certain a certain frequency band along which the light ray would transmit. So that particular frequency band would correspond to a wavelength band, and that's what is given by d lambda. Fine. So the group velocity is given by I think this part is what is the group velocity. Fine. The phase velocity, if you remember, in an earlier page we had the phase velocity as omega by beta, and that omega by beta, if you look at this, yeah, if you look at this, omega by beta reduces to n1 by c. Sorry, c by n1. Omega by beta reduces to c by n1. So that's how we have this phase velocity, and the group velocity is given by d omega by d beta. In order to exactly find out what would be the group velocity, this component d lambda is introduced. Okay, and by introducing this, I hope you're able to understand this. Omega is d by d lambda. If you look at this, beta is n1 2 pi by lambda. Here you can say lambda is n1 2 pi by beta, right? And from that you can get d lambda by d beta. Okay. Fine. That's what is this, d lambda by d beta. Okay. The first expression here, this corresponds to d omega by d lambda, d by d lambda of omega. I think you should take up a pen and paper, and you'll be able to find out what is the actual relationship. So this is what is the final group velocity, and this is what is known as the group index, the group index of the waveguide. If you're not able to understand this derivation, you can put it on Google Classroom. You can open it up as a discussion, and we can take it up in one of the other further classes. Okay, so it's almost time. Now I would like to, this will take up in further classes. So I would like to know what all you have understood and what you have not understood. Anything I can clarify right now? Anybody wants any clarification on any part of the topics that we have discussed today or yesterday? Okay, so and this these are the starting classes. So as we go along, we will be having small quizzes. A quiz as in a single question. I'll be posting questions along the duration of the in between the class. So that would give me a better understanding of how much you're actually understanding from the class. Okay. If you do not have anything more to discuss, you can leave the meeting, or you can wait for if the I don't know what is the link for your next class. Anyway, so our next class would be on Saturday morning at 9. I hope you all are aware of that, right?
Yes, sir.
Yeah. So Saturday morning at 9, we'll go ahead from this. Okay.
Thank you, sir.
Okay.
Thank you, sir.
I'm online. If anyone has any query, you can pose them.
Okay, thank you, sir.